Well, good morning, dynamic students. This is Professor Hagmeyer. I'm actually not going to be there on the first day of class on Tuesday, so I wanted you to watch this short video, which will kind of help introduce the course, and we can get started on some of the technical content. I will be returning on Thursday, and we can meet each other face-to-face at that time. But first I want to talk about the Blackboard site. You've already received an announcement regarding the textbook, so you should be looking at that announcement in the announcements page if you have not already. But let's look at the course content page, or the course content area. Here you'll find the syllabus. You should be looking at the syllabus and some other things from guidelines and emergency kind of preparedness in this area. You'll also see the schedule for the course. In the schedule for the course, you'll notice that we are having evening exams, and they're on 3 Wednesdays through in the semester. So those will be at 6 p.m. on those Wednesdays. And if you would plan now for those exams and try to set the time schedule the time in your calendars right now, then we won't have any issues. If you have another class during that time, then we can make other arrangements for you to take those exams at a different time on those Wednesdays or some other day close to that. If you look at the Assignments tab, here you'll find basically the schedule for those particular assignments, and what homework number 1 will be due on the 21st of January, which is a week from Tuesday, or the first day of class. You'll also see the homework format, and there you should see the first homework assignment, which is right then. You'll get used to this format, I hope. Then if you'll look at the next tab, which is class notes, what I will do is print, or allow you to print, the class notes for each chapter. You should print those, or if you're taking notes on a tablet or a device, then you can use these PDFs to take those notes. But in general, this will be the way the course will be structured, is that the classes will be on Tuesday and Thursday. What I'd like you to do is read before class these sections of the textbook and watch these videos. These videos are on the next page, or the next tab, which are right down here. And these are pre-recorded videos. These are YouTube videos. And for Tuesday coming up, you should watch those 2 videos in preparation for this lecture. For Thursday, you should watch those videos. As we go along, these videos are not required in terms of some students find them very helpful to watch them before class. I recommend that you watch them before class. It helps you get ready for the content that we'll be talking about during the class. If you don't get around to watching them beforehand and you want to watch the videos after the class, that might make some sense too. For today, or for this Tuesday, basically I'm asking you to watch these videos since we're not going to be there. There may be some explanation of some of the content there that I won't, obviously I'm not going to be there in class, so that would be helpful or important for you to understand. So if I were you, I would watch those 2 videos before Tuesday and watch all 4 of these before Thursday as we come up. All right, let's get started with the technical content of the course today. This is, again, will be in video 12.2, so I'm not going to go through this very carefully with you. But if you just remember from statics, some of the forces is equal to 0, some of the moments are equal to 0, and that's because acceleration is equal to 0. But however, in dynamics, acceleration is not equal to 0, so the sum of the forces is equal to the mass times acceleration, and the sum of the moments is equal to I alpha. For the first half of the course, we'll be focusing only on this equation and various forms of that. When we get to the last half of the course, we'll be talking about the mass moment of inertia, and we'll be dealing with this equation some more. The first half of the first half, we'll be talking about particles, and then we'll be talking about rigid bodies at the last half of the course. Particles are negligible size and shape, but they do have mass. Now, Newton's equations were, Newton defined motion with these two equations. A is equal to, or acceleration is equal to the change in velocity with respect to time, and velocity is equal to the change in position with respect to time. And these two equations can be manipulated in a variety of ways, and each one of these terms can be manipulated algebraically. So we have really 5 terms that can be changed around and moved into different positions and to solve the problem or the puzzle in a variety of different ways. For example, you can solve this one for dt and this one for dt, and then you can set those two equal to each other. And so you have this term equal to that term, and then that forms this equation called ADS is equal to VdV. When you do that, then you can solve the problems in a lot of different ways. So we're going to come back to this form. For right now, let's just look at A and V as functions of time. If you have velocity is equal to 20 minus 0.01 t squared, and you want to find an expression for acceleration, you basically just say A is equal to the derivative of the velocity with respect to time, so dv dt. So what you do is you take the derivative with respect to time of velocity. Here's velocity. So basically it's just the derivative of this. So the derivative of 20 is equal to 0. Derivative of minus 0.01 t squared would be minus 0.01 times 2t, which is what we have here. And then that's our expression for acceleration. If we want to find an expression for position, we'd say dt is equal to up here, velocity is equal to ds dt, and we could just pay the s on the one side and then v dt on the other side. So it looks like that. And then we can integrate both sides. You can integrate 0 or ds from s naught to s, and then putting this expression in here for velocity and integrating this, then we can see that this is going to be our expression for position. A couple of things. Position and velocity and acceleration can start at anything really, but in general they will start at s naught, v naught, a naught, something like that. Time will always start at 0. So whenever we're doing an integration or an integral, then you can count on in this course that time will always start at 0. All right, here's just another example. Here we have acceleration is equal to 10 minus 0.1 t. And let's say we want to find expressions for velocity and position. And some conditions. Velocity is equal to, or we may want to find, first of all, we're going to find expressions. Then we want to find a specific thing. We want to find velocity when t is equal to 3 seconds. And here is our conditional situation. At t is equal to 2, velocity is equal to 4. So how do we get started? Well, first we note that acceleration is a function of time. And we know that conditions are required to evaluate integrals. And then otherwise noted, which never, we will assume that t naught is equal to 0. Velocity, acceleration, and position may not be 0 at time is equal to 0. So let's just see what happens in this particular case. Here I have an expression for acceleration. If I want to find an expression for velocity, I might look at this equation. A is equal to dv dt. I'm going to put dv on the left side and a dt on the right side. I'm going to substitute this in for a and then integrate. I'm going to integrate this from v naught to v and integrate this side from 0 to t. I can integrate this from 0 to t because you can see that once I put the acceleration term in here, all of the terms over here are in terms of time, so I can then integrate this from 0 to t. Anyway, you can do that integration, you can see how it works, and then you can get an expression for velocity. If I want to find an expression for position, I might start with v is equal to ds dt. ds would be equal to v dt. ds is equal to v dt. Now that I have an expression for velocity, I can just plug that into this part. And so now I have this v dt. Integrating both sides, I got s naught to s. Time again only goes from 0 to t. And then I have this expression for position when I re-evaluate it all. So what I'd like you to do on these equations and these things is kind of go through them, make sure that you understand how to use them and that you're comfortable with using them in this way and that you get pretty fast. The biggest problem most dynamic students have is they struggle with the setting these things up, and I find that if you just do a lot of problems, you just get a lot faster. You just get a lot better, a lot more comfortable with them. So I will assign some homework problems. In general, I will say that in general, homework problems are not enough practice for many students. So the book is full of very simple, fundamental, and preliminary problems that will give you some of the practice at doing some of these basic integrals and derivatives, and I would go through those and just spend a few minutes kind of getting some practice at some pretty straightforward, some pretty easy ones. Then the homework problems won't be quite as challenging, I think. Anyway, now I have expressions for velocity and expressions for position. Let's go back and see what we were asking for. We want to find a velocity when t is equal to 3 seconds with the condition that at t is equal to 2, v is equal to 4. So let's see what we can do. At t is equal to 2, v is equal to 4. Well, can I discover something? I'm going to put, let's see. Here's my expression for velocity. So I'm going to put velocity is equal to 4 when t is equal to 2. I'm going to plug all those things in there, and here I can solve for v naught. When I solve that for v naught, then I can find out what v is at t is equal to 4. So again, if I started here, I wouldn't have gotten anywhere because I didn't know what v naught was at the beginning of the problem, or at the beginning of the v naught is whatever. Yeah, v naught would be at the beginning of the problem. I didn't know what that is, so this way I can solve for v naught, plug it back into here, and then I can find out what v is equal at t is equal to 3, or what velocity is equal to when t is equal to 3. So that's kind of the way you go about setting those things up. The next thing we're going to talk about is rectilinear motion, which means motion in one dimension. This is also explained pretty well on video 12.2, so I'm actually not even going to go through that with you. I just want to refer you to the video, and you can, most of these notes are pretty close to the same. When we get there, here's an example that we would do in class, or we would have done in class, where here's a velocity, and we want to find an expression for position. This is what I'm saying here. Find position s, or position as a function of time. And then here's a condition. Evaluate s when t is equal to 4. All right, to find an expression for position. Here, velocity is a function of time. V is equal to ds dt. I can rearrange that into ds is equal to v dt. And I can integrate both sides. I'm going to plug that into here and integrate it. And you can see how it goes pretty quickly once you get some practice. Here then is our expression for position. Now in this case, I integrated from s naught to s, but it said that right here, at t is equal to 0, s is equal to 0. When that is the case, s naught right down here is equal to 0, so it doesn't show up, or you don't need to have it show up in the equation for position. Once I have an expression for position, then I can evaluate it at any point. In this case, t is equal to 4, or where t is equal to 4, I can evaluate that and see that s is equal to negative 32. Well, what's going on here? Sometimes it's helpful to build a table and to draw a picture of the motion. And so that's what I've done here. I'm going to say that at t and v and s, I'm just going to build a little table. We found that at t is equal to 0, v and s are both equal to 0. And what we solved for in this thing is that t is equal to 4, s is equal to negative 32. So that's what this is all about, or at least that's what this is about. If I want to find out the velocity at t is equal to 4, well, I have an expression up here for velocity is equal to, or for velocity as a function of time. So I could plug t equals 4 here and find out what the velocity is, and it is also equal to negative 32. Plugging the other pieces in here, or those other times, I can fill out this little table, and you can kind of see what's going on. it starts at here. As this is a position line. As time becomes, or as time marches on, the particle is moving in the forward direction, so that at time is equal to 1, it is moved up to position 1, moving in this direction. But here's kind of the curious thing. When time is equal to 2, the position is back at 0. So something happens here, and you can see that where right here happens, this is time 2, and position, or time is equal to 2 seconds, and position has gone back to 0. So again, something's happened. It basically turned around someplace. When time is equal to 3, then position has gone to -9, and when time is equal to 4, position has gone to -32. So you can tell by the table that the velocity changes direction someplace between t1 and t2, or between 1 and 2 seconds. So what is the value of the velocity when it changes direction? So again, you can kind of see just by watching the cursor what's going on, but it goes up this way, and then as it turns around, then it starts going that way in kind of a hurry. Well, when it turns around, the velocity is equal to 0. And that's a truism that you kind of need to know, but you can see what happens here in this table. You can kind of see what happens in this position line. And you can understand that the velocity, where the position, I guess the travel, the velocity changes direction, goes from the velocity being in a positive direction, and then it starts going in the negative direction. At that transition point, velocity is equal to 0. So how can you find out what the time is when it changes direction? Well, if I have an equation for that, I can just say where velocity is equal to 0, I can solve that for the time, which indeed I did, and I can say that it changes direction at 4/3 of a second. What is the position or the displacement at that point? Well, I should have an expression for position right there. Plugging 4/3 into there, I can find out that that happens at s is equal to 1.185 meters. Now, a couple of things that are related to this that might be easy to understand and might not be. But by the end of the problem, what is the distance traveled? Well, the distance traveled is the total distance. So it has gone this way and then this way. So you have to add up this whole thing. In other words, this distance from here to here added to this distance from here to here. And that's the total distance traveled, which is 34.37 meters. The average speed is the total distance traveled divided by the total time, and that is 8.59 meters per second.